Hello, I'm Timothy Rivette, and my midterm on material selection is on trusses. The title of the paper that I was assigned is Simultaneous Material Selection and Geometry Design of Statically Determinate Trusses Using Continuous Optimization. The authors are Saurav Rakshi and G.K. Anantha Suresh. The journal was received on June 6, 2006 and revised on December 28, 2006, and it was published online on April 5, 2007 by Springer Verlag, and it is 14 pages long. The specific scope of study is on optimization framework, which considers geometry and materials simultaneously, a design index which helps choose the right material, and it has some limitations as well, like single loading and statically determinate trusses. The key question addressed is how do material selection and geometry selection work together to get the most optimal outcome? On the left you can see a geometry of trusses, and on the right is a Ashby plot to determine material. The model used is a continuous optimization model. It takes into account tension and compression to reduce yielding and buckling. It minimizes strain energy on the trusses, and it also uses an FEA to determine failure modes. The strength-based index first is found using density over tensile strength. A stiffness-based index is used by using density over the Young's modulus squared. And finally, a design index is used by it's the ratio of compression to tension. The materials surveyed use three main criteria: strength to weight, stiffness, and cost. Some materials considered on this are concrete, wood, aluminum alloys, and low alloy steels. The key research question from the study, the first key research question is how do load conditions affect material choice? First, which application are the trusses used for? Is it going to be a low load, a moderate load, or a high load? This graph shows the design index on the x-axis, and the top plot has density on the y-axis, and the bottom has Young's modulus. As you can see, low loads concrete is more fit for low loads. Wood or aerated concrete are more fit for moderate loads, and low alloy steels are more fit for high loads. The second key research question is how do we determine materials based off of tension and compression? First, an equation for tension to find the cross-sectional area is the applied tensile force over the tensile strength of material. And on the other side, compression, the optimal cross-sectional area, is found by the square root of the shape factor multiplied by the effective length of the member squared multiplied by the applied compression force, and that is over pi squared times Young's modulus. Some important materials taken away from this are the optimal material depends on if truss is receiving more compression or tension. If it's receiving more compression, you want materials with a high stiffness to density ratio, and if it is receiving more tension, you want materials with a high strength to density ratio. This Ashby plot shows the density on the x-axis, and we have a y-axis with strength to density, and a y-axis with stiffness to density. As you can see, concrete is more towards the bottom, which correlates with a lower load. Towards the middle, we have wood and aluminum alloys, which correlate with a moderate load. And finally, at the top, we have low alloy steels, which is the most fit for a high load, as we can see right here. In summary, key conclusions from this research paper include that simultaneous material and geometry optimization ensures maximum stiffness, minimal weight and cost, and it provides safety against failure. The material selection based on the load conditions defines the most useful material for low, moderate, and high loads. And the impact of tension versus compression on material choice defines most useful material based on tension and compression. Some critiques I have of this paper are that it has real world applications which are backed by data. One limitation, though, is that it is limited to only single static loads. It doesn't address statically indeterminate structures, which are more common in real life.